Hello and welcome back to Multidimensional Integration, the video series where we talk a lot about different integrals in Rn. And indeed, in today's part 13, we will go one step back and revisit our general n-dimensional Lebesgue measure. More precisely, we will discuss and see that this one is a so-called regular measure. But before I tell you what this actually means, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And as a Steady or Patreon member, you can use the link in the description to download a lot of additional material for the videos. And now without further ado, let's immediately discuss the Lebesgue measure on Rn again. In fact, we can quickly recall the general construction idea. The starting point is simply that you already know how to calculate the generalized volume of a cube in Rn. And then we can also stretch it in different directions and calculate the volume of a generalized rectangle. So here I will always say rectangle because my pictures are two-dimensional, but please don't forget, we actually have n different directions. So in short, what we have here is just the Cartesian product of intervals. And it turns out that it is really useful to have the interval closed on the left boundary, but open on the right boundary. Obviously, the volume of the rectangle does not care about if the boundary is included or not. So now this is what we call a rectangle, and obviously this is a good choice because there we don't have any doubt what the Lebesgue measure of the rectangle should be. Namely, if we call this generalized volume mu, then we know it should be given by multiplying all the lengths of the sides. So by using the product symbol, this formula gets quite short. We just have the product over bi minus ai. So this is the whole thing, and this is well defined for every rectangle in Rn. And you can check out my measure theory course to see that this is what we usually call a pre-measure. It's not a full measure yet because it's just defined on a semi-ring of sets. And I denote this by a curved R because this one should include all these rectangles. So it's just the collection of all these rectangles, and you can see if you form an intersection of one rectangle with another, you get out a rectangle again. And here I will not tell you more about the properties of a semi-ring because they are all stated in my measure theory course. Indeed, here we just want to use a famous result from measure theory, which is known as Kara-Theodory's extension theorem. And in fact, the whole thing is not so complicated as it sounds, because we can immediately write down the extension of our pre-measure mu. This will lead us to a map phi that is defined on the whole power set of Rn. And again, in measure theory, this extension is what we call an outer measure. And this one can be a little bit confusing, because in general, this is not an ordinary measure as we want it. However, we can always form a suitable restriction to get out the measure as we want it, and this will be the Lebesgue measure on Rn. But first you should know the definition of our phi here. It's defined for any subset A in Rn. And the definition is in fact quite visual, because we can just cover any set A with rectangles. So if that is our set A, we just take enough rectangles to cover the whole set. So the whole picture might look like this. And now let's call the rectangles we choose here just Rj. And the condition we want to have here is that the union of all these rectangles is a superset of A. And maybe finitely many are not enough, so for every natural number, let's fix a rectangle Rj. And with that you already see, we have an upper estimate for the actual volume of our set A. This is clear because every single rectangle has a well-defined volume given by mu of Rj. And then we just add up all these volumes, and maybe it's a finite number or infinity. So this is the whole idea. We have a lot of different choices for the rectangles, but we always get out an upper bound for our volume of A. Hence it makes sense to go to the lowest possible upper bound, which is the infimum of this set. The infimum in the real number line is always well defined, and here in the worst case we would also get out infinity. And that's already it. This is the whole approximation idea for the Lebesgue measure in Rn. And now in the next step you just define the Lebesgue measurable sets as a subset of Prn. And if we just call them Lrn, then we have our n-dimensional Lebesgue measure lambda n. And this whole procedure of starting with just a pre-measure, going over an outer measure to our actual measure we want, is known as Carat-Theodory's extension theorem. And indeed, this is quite helpful because this nice formula for the outer measure is still valid for our Lebesgue measure. Simply because the Lebesgue measure is just a restriction to a smaller subset. And you know, we really need to do that because we want to have a sigma algebra and all the nice properties of the Lebesgue measure. Okay, so this was just a reminder how the Lebesgue measure is constructed, but it still helps us to understand the property we discuss now, which is known as regularity. Indeed, we can do a similar approximation of the volume, but not with rectangles, but with general open or compact sets. So this is something that definitely works in Rn, because we have all the notions like compact and open sets. So let's split this result into two parts, where the first part should concern the open sets. This is called outer regular because we want to cover this set with open sets, so we come from the outside. So let's say we start with a measurable set A, and now we take an open set which is a superset of A. So this is definitely always possible, and then we can take the Lebesgue measure of our open set U. And then as before, we have a whole set of possible values. So the picture is quite similar. We have our set A, and then we want to cover it with an open set U. And now, as this picture suggests, we can make it closer and closer to A itself. Or in other words, also here, we want to go to the infimum of the possible Lebesgue measures of U. So again, this is a well-defined number, and if this one is actually equal to the Lebesgue measure of A, we have what we want. Indeed, it tells us when we know what happens on open sets, we already know the whole measure. So an approximation with open sets from the outside works for this measure. So the Lebesgue measure in Rn has this nice property, but you can already remember not every measure is autoregular. But still, for the Lebesgue measure here, it seems to be a natural property. But of course, I will show you a proof of that such that you can believe me. But first, I also want to define the term inner regular. This has a similar idea, but now instead of open sets around A, we take compact sets that lie inside A. Hence, the measure of the compact set K should always be smaller or equal than the measure of A. So the only thing that changes here in the formula is the subset relation. And please note, for us it's always possible to satisfy this subset relation because the empty set is a compact set in Rn. Therefore, the set of possible values here is definitely not empty. And now, since we come from the inside of the set A, we want to look at the supremum of these values. And if this supremum is actually equal to the measure of A, we say that our measure is inner regular. So you see, we have two approximations here, one from the inside and one from the outside, and if we have both of them given, we would speak of a regular measure. So the nice result here is that our common n-dimensional Lebesgue measure is a regular one. And since this is a property that can also be useful for calculating some special integrals, I definitely wanted to state it here. And for the same reason, I want to show you the actual proof of that, but this will be done in the next video. So I really hope I meet you there again, and have a nice day. Bye bye.